Welcome to this course on power quality. So, we now will discuss the numerical problem of on this nonlinear load which caused the power quality problem. So, starting with the first numerical examples. Consider the single phase uncontrolled bridge converter shown here in figure below with the sinusoidal input supply voltage of 230 volt and constant DC load current of 12 ampere. Calculate the CF means crest factor, DF distortion factor, DPF displacement factor, D power factor and E for percentage TAD. And you can see, this is typically diode rectifier with the RL load with the highly inductive circuit. So, you have a supply voltage, supply current will be square wave and the voltage across the load here will be of this kind of waveform and current will be as it is a square wave. So, it is a this square is because of this constant current flowing into the load like that. So, coming to numerical part of it, the given that supply voltage is 230 volt, frequency 50 hertz and DC link current of 12 ampere. So, supply RMS current in case of square wave if you take a like integration and take average, it comes same as the your typically of DC side current. So, it is 12 ampere and the fundamental of this square wave is 4 upon pi into I, that is the peak, but divide by root 2 if you take it. So, it becomes 2 root 2 by pi into I 0, that is your fundamental RMS current and comes by calculation it comes 0.9 I 0. So, 0.9 into 12 it comes your 10.804 ampere and the crest factor of supply current which is defined as supply peak current divided by supply RMS current. So, it will be I peak upon I RMS. So, it will be I 0 plus I s. So, it will be 12 by 12 means it is a 1. So, crest factor of this is 1, however, the sine wave have a crest factor of 2 1.41. So, crest factor of this wave non sinusoidal wave is only 1. So, displacement factor we define like a fundamental divided by total RMS, fundamental RMS divided by total RMS current and we keep the value from here which we calculated 10.8 divided by 12. So, it comes 0.9 and displacement factor that is here cos phi 1. It also called phi 1 is the fundamental the angle difference between the fundamental voltage fundamental current and in this case that angle is 0. So, cos theta 1 is 0. So, it becomes your displacement factor cos phi theta 1 equal to 1 and power factor that is PF equal to DF into DPF is a 0.9 into 1. So, it is a 0.9 and the total harmonic distortion of supply current typically is your IGC square minus IS 1 square power half means square root divided by IS 1. So, keeping the value of this it comes 0.4843. So, it is a 48.43 percent total harmonic distortion of this square wave. Coming to a second example like of this nonlinear load, a single phase uncontrolled bridge converter shown in figure has a RE load with the resistance of 2 ohm and the battery voltage of your 150 volt. The input AC voltage is 230 volt at 50 hertz and calculate the load average current, that is typically the I 0, average of that supply RMS current that is I s and typically you can call it the crest factor, CF crest factor, distortion factor, displacement factor, power factor and percentage TAD. So, after putting the value the waveform of supply voltage we take a sine wave, the current will be drawn only when supply voltage is greater than the value of E. So, current will be drawn only for this period and this is the output voltage it will be equal to the battery voltage only when it will be more when the supply voltage is more and this is the kind of the current will be flowing into this like So, you will find supply current is only drawn only for the period of this like or so. So, it is a peaky current but the fundamental is in phase with the voltage like also. So, coming to the the numerical part of it, given that Vs equal to 230 volt and Vsm peak of the supply voltage is root 2 into 230 that is 325.27 and frequency f equal to 50 hertz and load equal to R equal to 2 ohm and E equal to 150 volt. So, in single phase diode bridge converter with the RE load the current flows from angle alpha when AC voltage control is equal to the E, AC voltage equal to E and the angle beta at which the AC voltage reduces to E. So, from the relation we can call it like a Vm you can call it sin alpha equal to E. So, from this we can find out E, putting the value it comes 27.86 and beta will be pi minus alpha. So, it comes like here it is start the current, here it is ceases the current. So, it is a pi minus alpha, that is 152.54, and the conduction period, I mean it is a beta minus alpha. So, out of 180 it is only typically 125.08. So, that much conduction is there of degree in this typically. The active power drawn from AC means will be P equal to I s square plus E 0 E I 0. So, putting the value, the active power comes your 482.98 watt, and fundamental RMS current drawn from AC mains will be P upon V s, that is 49.93 ampere, and supply, typically the supply AC peak current will be your V m minus E, because it is only flowing for that period, divided by the 2. So, it is your peak current will be peak of this, that is the peak voltage of supply minus E divided by the 2, I mean because that is the typically the resistance there 2 ohm. So, it comes 87.635, and the load average current, I mean you can calculate from the this kind of waveform which is shown in the previous slide. So, it comes of this formula, it comes 39.715, and RMS of supply current is the RMS of discontinuous current of AC mains, typically of relation of RMS calculation. I mean you will find this derivation formula certainly in power electronics, or you can derive it. So, it comes 52.563. So, crust factor is here peak upon RMS, total RMS. So, it is I peak I s. So, it is a 1.66725. This factor, crust factor is more than root 2 of sine wave, that is 1.41. So, it means this is the peaky current, that is the region crust factor is more than your root 2 or 1.41. Coming to distortion factor, that is I s 1 upon I s. So, I s 1 fundamental RMS current we have already calculated 49.926 divided by 52.561. So, it comes typically like your 0.95. I mean because of harmonics, I mean distortion factor in sine wave is 1, and here it is reduced to 0.95 because only presence of harmonic, and displacement factor here it is 1 because the fundamental current and fundamental voltage, I mean they are in phase. So, your theta 1 is 0. So, that is cos theta 1 equal to 1, and power factor is typically P upon V s I s, that is 0.95, that is multiplication of both also, that comes that, and total harmonic distortion of AC mains current is I s square minus I s 1 upon I s 1. So, putting the value of this, we get the THD here 32.928. However, this THD is lesser than what we have typically in case of your square wave, that was 48% like or so. Coming to numerical example 3, a single phase outbridge rectifier shown in the figure is drawing the AC current at 0.97 displacement factor, and THD of the AC current is 60%, is drawing 2000 watt from the 230 volt 50 hertz AC source, and crust factor is 3 of AC current. Calculate the power factor, RMS current and peak current. So, you can see here the capacitor is there, and you will drawing this kind of the current only for the duration when AC supply voltage is more than the capacitor voltage. You will be drawing the current for very short period when the capacitor is getting charged, and when it comes to this kind of current, and this is the load current. So, it will be drawing current into this here will be only for short of the period. So, you can see this kind of current. Now, question is why it is this displacement factor is 0.97. That may be because of the two reasons. One is the source impedance, that may cause this to delay it, or another reason sometime it is that is to starting conducting little before because of discharge. So, it may be slightly leading or it can be lagging, depends on the source impedance parameters like also. So, coming to the solution part, numerical part of this, I mean given that V s equal to 230 volt, frequency 50 hertz, THD of supply current 60%, active power drawn is 2000 watt, displacement factor, I mean dPf cos theta 1 is given 0.97, crust factor is given 3. So, you can call it the distortion factor, relation between distortion factor and THD is 1 upon under root 1 plus THD square. So, once we know the THD, that is 60% means 0.6 you can keep here, and you will get a distortion factor 0.851. In sine wave it could have been unity. Now, power factor is a dPf and dF. So, it is keeping a value of both, it comes 0.832, that is the power factor. I mean that is a power factor formula in case of your power electronics or distorted environment like and supply RMS current will be your P upon RMS voltage into power factor. So, that is you are keeping the value, it comes 10.54 ampere. So, peak current of AC means that is crust factor into RMS, so 3 into 10, I mean typically ampere. So, it comes 31.369. So, that is the that much peaky current is drawing such kind of typically kind of the you can call it load with the capacitive end. So, the such kind of load are in practice many load which have a capacitor diode rectifier by followed by capacitor filter, and this TAD crust factor and TAD depends on the relative value of capacitor and the load time constant, means that is a typically equivalent load resistance like. Coming to another example, typically consider single phase semi controlled bridge converter with a sinusoidal supply voltage of 230 volt 50 hertz and constant DC load current of 20 ampere. Calculate the distortion factor, displacement factor, power factor, total harmonic distortion of supply current for output voltage of 0.5 into VDC, where the VDC 0 is the output voltage at firing angle 0. Repeat this part for fully controlled bridge converter, where typically all 4 are the thyristor like. So, if you look into this case semi converter, you will have a current drawn at alpha, but it will finish at the angle of 180 degree. You start from again pi plus alpha and finish at 2 pi. So, that kind of current you will draw, I mean like, and this is the kind of output voltage when the your typically thyristor conducting, because it is a highly inductive current, you have a DC current here, and the output voltage will be only when your thyristor is connecting the supply into the output like. So, coming to numerical part of it, given that the supply voltage 230 volt, F is 50 hertz and I 0 equal to 20 ampere, in single phase semi converter control converter, I mean like the waveform of supply current is from firing angle alpha to 180 degree with the amplitude of DC current I 0. So, we can find out from typically if V 0 equal to 0.5 where alpha, from this relation alpha equal to 0 with 90. So, we can find out it comes from this relation alpha 90 degree. So, RMS current now we can find out from this relation, in this case putting this value, it comes the RMS current comes 14.142 ampere, and fundamental RMS current from this relation if you put all this value, because in semi converter, so it is a your fundamental will be crossing alpha by 2. So, it will be keeping the value, it comes 12.728 ampere. Displacement factor cos theta 1, that is cos alpha by 2 in semi converter with constant DC current. So, it comes 1 by root 2. So, it is a 0.7071, and distortion factor, that is 1 upon TAD square, it comes 0.9 typically, and we can typically find out now power factor, that is DPF and DF. So, keeping the value, it comes 0.63639, and total harmonic distortion, if you keep the value of total RMS fundamental RMS divided by square under root of that divided by your fundamental RMS. So, it comes 48.43% like also. Coming to case second part of it, if this is fully controlled converter, now all 4 thyristor and typically the firing angle is 60 degree. So, you will have a, in case of thyristor converter, a square wave, okay, but phase shifted by 60 degree, and this kind of will be the voltage waveform, I mean, and this is your output current. So, square wave of current will be there. So, the waveform of supply current is from firing angle alpha to pi plus alpha with the amplitude of DC current, and if V equal to 0.5 VDC 0, the VDC 0 DC current at alpha equal to 0 and alpha. So, we can find out typically the square wave RMS will be only same as the output load current, that is a 20 ampere, and the fundamental supply current will be 2 root 2 upon pi, that is 0.9 into I 0, that is typically 20 into 0.9 18 ampere, and displacement factor is cos theta 1, that comes cos alpha in case of fully controlled converter, that is typically value keeping this cos 60, here it comes like half. So, that is 0.5, and distortion factor now 1 upon 1 plus TAD square, I mean it is 0.9, and power factor here will be your distortion displacement factor, distortion factor keeping value of this, it comes 0.45, and total harmonic distortion we put the value IS square minus IS 1 upon IS 1 under root of that. So, it becomes 0.4843, that comes 48.43% like because of a square wave. So, coming to another example, a single phase example number 5, a single phase fully controlled bridge converter shown in this figure is used as a line commutated inverter to feed the power from battery with a 180 volt and an internal resistance of 0.2 ohm of typically this, and supply RMS voltage is 220 volt. So, and a sufficient inductance is included typically in the output current to maintain the virtually constant current of 10 ampere, determine the required delay angle of the thyristor, the distortion factor, displacement factor, total harmonic distortion current, crust factor of current, power factor, and AC RMS current. So, after making the model and putting all the value, the waveform like of current for thyristor converter but this current is constant, it comes a square wave where the load current is constant and corresponding that typically it is charging the battery, it means it is, you can call it, is feeding the power here. So, you will find the voltage will be negative. So, it is working as an inverter, I mean like LCI, it is working as inverter, it means the battery power is fed to the typically towards the AC grid, like I mean. So, it is working as a line commutator inverter, like that is why it is a negative voltage, positive current. So, you will have a negative power on DC side which is fed to the grid, like. Coming to the numerical part of it, given that Vs equal to 230 volt, F equal to 50 hertz, I 0 10 ampere and E equal to 180 volt and resistance 0.2 ohm. So, our supply RMS current will be like a square wave, will be same as the DC side current. So, typically I mean like it is a comes to about 10 ampere, okay. Then it is a RMS fundamental will be 0.9 I 0 is a 9 ampere and the average voltage will be like your 2 root 2 upon pi into V s cos alpha, that will be 0.9 V s cos alpha, and it will be equal to minus E minus I 0 R DC. Putting the value of this, we get the typically of this minus 178 and putting the typically the value, it comes your 154.03 degree, that is for inverter operation because it is more than 90 degree, like I mean also. And distortion factor will be 1 upon THD square. So, keeping a THD here 0.4848, so it comes 0.9, and displacement factor cos theta 1, that comes cos alpha, putting the value it comes minus 0.899, and power factor will be your displacement factor and distortion factor. The distortion factor is so it comes 0.8091, and total harmonic distortion because it is a square wave, putting the value it comes like a 48.43, and crush factor is a peak upon RMS, that is 1. So, in this case also crush factor is 1, which is less than sine wave it is root 2 1.41, like. So, coming to another example, a single phase AC voltage controller shown here in figure is used to control the heating element of maximum power of 3 kilowatt from the single phase AC mains of 230 volt 50 hertz. If power is to be controlled to deliver 1 kilowatt, calculate the load resistance, RMS voltage across the load, supply current RMS and power factor. So, after putting the values, then you can see how the supply current is. This is supply current, this is the typically the, you can call it like a output your voltage across the load in both the half cycle because it is a AC controller, and that is the current, like. So, supply current and load current are same because it is a series one, but you will have a certainly here harmonics as well as reactive power pattern. So, coming to the calculation part, your Vs is 230 volt 50 hertz and maximum power is 3 kilowatt and the power after control is 1 kilowatt. So, you can find out load resistance from maximum power, putting the value here. So, it comes 17.633, it is a 230 and it is you keep the value of 3 kilowatt, and the RMS voltage across the load will be ISRS. So, putting the value it comes like a corresponding to 1 kilowatt, you keep the value of 1 kilowatt and resistance is already there. So, it comes 132.789 after the control to 1 kilowatt power only, and supply RMS current is P under root P upon R. So, it is a 7.531 and the supply power factor will be P upon VSIS. So, it comes 0.577, and this reduction in power factor is because of harmonics as well as reactive power. But coming to another example of this is single phase AC voltage control, so one has a resistive load of 10 ohm, the input voltage 230 volt and delay angle of thyristor is 100 degree. Calculate the load RMS load voltage, power consumed, displacement factor, distortion factor, total harmonic distortion of AC mains current, power factor, crush factor of AC source current and AC source RMS current. So, after keeping the value of alpha equal to and simulating, you will find this kind of the waveform for typically of supply current, then load voltage because it is a resistive load, and then this is the output current because they are in series, so both will be the same. Coming to numerical part of this, given that supply RMS voltage is 230 volt and frequency is 50 hertz, resistance is 10 ohm and firing angle of the thyristor of AC voltage control is 100 degree. So, in single phase control AC controller, the waveform of the supply current has a value of Vs upon Rs from angle alpha to pi. So, you can just calculate the peak like 230 into root 2, that is 325.27, and AC RMS current from this relation, that is Is equal to Vsm in bracket 1 upon 2 pi r and in bracket pi minus alpha plus sin 2 alpha by 2, square root of that. So, it comes 14.363 ampere, and fundamental RMS current from this relation, I mean it comes like 11.44, and the theta 1 we can calculate the typically from this relation, I mean from from fundamental relation, so it comes 38.3656, and fundamental active power drawn now Vs IS1 into cos theta 1, putting the value Vs IS1 cos and theta 1 we got it, so it comes like a 2062.957 watt, and fundamental reactive power drawn by this formula Vs IS1 sin theta 1, it comes 1633.125 VR. Then RMS voltage from this relation corresponds to that alpha equal to 100, it comes 143.62, and active power drawn by the load is Vs IS1 on 2062, and displacement factor is cos theta 1, so it comes 0.784, and distortion factor IS1 upon IS it comes 0.79649. Total harmonic distortion, if you put the value of here, typically distortion factor it comes TAD of 75.91, and power factor comes typically of both multiplication of both of this at this, it comes 0.62445, and peak current will be VSM sin alpha divided by R. So, that is from this value it is starting. So, that will be the maximum value divided by R. So, it is 32.03 ampere, because it is after 90 degree. So, that will be corresponding to sin crush factor of supply current will be I peak upon IS, and AC mains resonance current if you put the value 14.363 ampere like. So, that is you can clearly see in this case you have a reactive power burden, because distortion displacement factor is also there, distortion factor is also there. So, and TAD is also substantial. So, you can call it here you have a reactive power burden as well as the harmonic substantial, and that is the reason you have a poor power factor. And the crest factor also here in this case it is more than root 2, that is more than sine wave, that is 2.23. So, this kind of the load is considered to be one of the very bad load which have a higher crest factor, which have a reasonable reactive power as well as the harmonics drawn from the supply system. Coming to another example number 8, a single phase 230 volt 50 hertz supply system is feeding a set of non-linear load which consists of semi control bridge and the diode rectifier connected in parallel. The diode bridge converter drawing 10 ampere constant DC current and semi converter drawing 15 ampere constant DC current at 60 degree fire angle of thyristors, and for this composite non-linear load calculate the active power consumed, reactive power consumed, displacement factor, distortion factor, total harmonic distortion of AC mains current, and power factor, crest factor of AC mains current, and AC source RMS current. So, you can see this kind of load that both are connected. One is diode rectifier with constant current, another is thyristor converter with constant current, and you can just see typically the what will the output voltage of diode rectifier, what will the typically the current of diode rectifier, what is the typically semi converter current, and what is the total current. The sum of these two, sum of these two current will be the total supply current, where the diode DC side current is there and this is thyristor DC current. So, you we will be considering this typically of this current like calculation. So, coming to the solution, given that the supply voltage is 230 volt 50 hertz, diode rectifier converter, diode bridge converter is drawing 10 ampere constant DC current, thyristor bridge AC DC converter is drawing 15 ampere constant DC current at 60 degree fire angle of thyristor. So, in single phase diode rectifier the ILD equal to I DC DC, that is 10 ampere, and ILD 1 that is 2 root 2 upon pi, that is a fundamental 4 typically of square wave, so it comes to 9 ampere. Moreover, the active component of AC mains diode current comes the typically same as 9 ampere. In single phase semi control converter, you can find out typically the AC RMS current from this relation it comes 12.247, and RMS of fundamental will be typically from this relation will be 11.691 ampere, and active power of the semi converter will be your ID1 TD1 into cos theta 1, putting value of cos alpha 2, that comes 10.125, and reactive power drawn from semi converter will be theta 1, that is alpha by 2, that 5.846 ampere. Therefore, total active power component of the AC mains current will be sum of the both, so that is 19.125 ampere, and total reactive power consumed here diode rectifier 0, this is only there. So, 5 and the active power drawn now from this fundamental active current. So, this is total power drawn 4398.75 watt, and reactive power is 144,504 VR, and now the displacement factor from your P upon S from P and Q you can find out. So, that comes 0.956, and distortion factor is computed by computing the RMS current and fundamental RMS current of the composite load. So, AC mains diode rectifier is a square wave, the displacement by, however, the AC mains current of thyristor bridge converter is also but phase shifted of 60 degree. So, RMS value of supply current will be combined load current consisting of diode and thyristor converter. So, if you look into from the waveform you can find out RMS value, it comes 21.213 ampere. So, RMS fundamental of this composite load you can calculate from virtually from apparent divided by voltage. So, it comes like 20 ampere, and distortion factor from fundamental RMS divided by total RMS it is 0.0943, and total harmonic distortion of the current is from RMS and fundamental RMS. So, you put the value, so it comes typically your 35.3%, and power factor of means it is going to be more than closer to sine wave than square wave, and power factor is dpf into df. So, putting this it comes 0.902, and crest factor of AC mains current is your peak upon RMS. So, put the value of addition of both peak plus divide by RMS, so it is 1.179, and AC source RMS current calculating from the relation which we calculated earlier, it comes 21.21 ampere. So, that is about single phase. Now, let us go to another example number 9 with the 3 phase. A uncontrolled 3 phase bridge rectifier shown in the figure is fed by line voltage of 415 volt, 50 hertz. If a continuous constant current of 30 ampere is in RL load, calculate the mean DC voltage, load resistance, load power, RMS AC mains current, distortion factor, displacement factor, power factor, and TID of supply current. So, you can clearly see here, and you will have a 3 phase supply current of this Cauchy square wave, which are of 120 degree duration, and they will be in the phase with the phase supply voltage, and this is output voltage, this is output current constant. So, coming to calculation for typically numerical part of this, given that the supply voltage is 415 by root 3 239.96 at 50 hertz, and the output current is 30 ampere. So, RMS of Cauchy square wave current with the 120 degree pulse width will be I 0 into root 2 by 3, that is 24.49 ampere, and moreover the RMS of fundamental component of Cauchy square I S 1 will be root 6 by pi. So, that comes 23.39 ampere, and active power drawn by the load which your 3 Vs I 1 cos theta 1, it comes 16.813, and average output DC typically from this relation it is a 560.446, and the resistance equivalent of load will be the voltage divided by current on DC side. So, it is 18.682 ohm, and load power 3 Vs I S 1 cos theta 1 is 0 again the same power like what we calculated 16.813, and RMS of Cauchy square wave current will be we calculate 24.49, and distortion factor will be I S 1 upon I S 3 upon pi, it is 0.9549, and displacement factor is cos theta 1, that is here alpha 0. So, it is 1, and power factor displacement factor, distortion factor is 0.9549, and total harmonic distortion of this current, putting the RMS total RMS and RMS of fundamental root of square of both in root that divided by I S 1, it comes 31.08, and you clearly see that because Kaplan are not there in this. So, it is reduces from square wave of 48% to 31.08% in case of this Cauchy square wave form. Coming to another example number 10, a 3 phase non-linear load is supplied from 3 phase 415 volt 50 hertz, and it consists of a diode bridge converter feeding resistive load of 30 ohm. Calculate the fundamental active power drawn by the load, power factor, RMS supply current, distortion current, fundamental RMS current, peak current of mains, and the total harmonic distortion of AC mains current. So, in this case you will find again the Cauchy square wave even with the, because voltage is almost continuous. So, you will get this kind of waveform. So, coming to numerical part of this, given that supply RMS voltage is 415 by root 3, that is 239.6 volt, and the peak of this will be of 338.85 root 2 of that, and frequency of 50 hertz, and resistance is given 30 ohm. So, you can find out fundamental active power drawn by the this relation, that comes 10.48843 kilowatt, and power factor comes active power divided by 3 Vs I S, it comes 0.955, and supply RMS from this relation you can find out for resistive load 15.2668, and distortion factor is I S 1 upon I S. So, it comes 0.955577, and the RMS fundamental component from calculating this relation it comes 14.59158 ampere, and peak AC RMS current, that is V peak upon R will be like a typically 19.56 ampere, and total harmonic distortion, putting the value of this it comes 30.77. So, it is little lesser than your previous case, like that is almost like a similar to that. Coming to another example number 11, a 3 phase non-linear load shown in figure consisting of a 415 volt 50 hertz 3 phase rectifier with very large capacitive filter, and its DC bus is supplying a DC power of to a voltage source inverter at 3-phase induction motor variable frequency drive at 540 volt DC with a total circuit resistance of 1 ohm. Calculate the average DC current, RMS AC supply current, RMS fundamental supply current, input active power, TAD of AC mains current, displacement factor, distortion factor, power factor and current factor of supply current. So, you can see, I mean, with this capacitor value you will get this kind of current waveform, which are 2 notches in typically in each half. So, Tuplan will not be there, but all 5th, 7th all harmonic well. So, this is for all 3 phases, and this is typically the DC link current and this is the DC link voltage because of capacitive filter. Coming to numerical part, we have a supply voltage of 415 by root 3 per phase 239, and we have a 50 hertz supply resistance on the load side is 1 ohm, and the voltage typically on the DC side is 540 volt. So, 3 phase diode rectifier with very large capacitive filter at the DC bus behave as a series resistance with back EMF RE load. So, AC supply current flows through 2 pulses of each half cycle from theta 1 to theta 2 and theta 3 to theta 4, when the segment of AC line voltage are equal to the greater than the E, that is 540 volt and is discontinuous. So, at angle theta 1 the AC supply current increases and it decreases to Cz to 0 at theta 2 when AC voltage reduces to E. Similarly, conduction period for second pulse of this supply will be from theta 3 to theta 4, and these angles are computed as follows. So, from this waveform alpha equal to sin E upon VSM, if you put the value of this from line voltage, it comes 66.94, and beta for this, I mean, like it comes 113.06, and the conduction period comes beta minus alpha, it is a 46.12 out of 60 degree, it is conducting only for this period. However, there are 2 angles for first pulse will be the reference for the first line, and the second pulse will be again calculated from the pi by 3 plus alpha. So, that will be 126.94 and delta equal to 4 pi by 3, that gamma, that is 173, and conduction period will be the same as 46. There will be 2 pulse of 46.12 compared to like your pulse of 60 degree. So, it is conducting only part of 60 degree pulses in out of those. So, out of 180 it is conducting around 92 degree, 92.24 degree only like. So, coming to how these angles are, I mean we have calculated will be correspond to theta 1 value, theta 2 value, theta 3, theta 4 value, and since these are 6 pulses for charging the DC bus capacitor in one cycle, all 6 pulses are identical. The DC bus, you can call it DC bus current, you can calculate from here from this relation. So, it comes 23.9682 ampere, keeping R equal to 1 and VSM root 2 into 415 and E equal to 540 in this relation. Since the AC mains current with a couple of pulses in each cycle is an odd and quarter symmetry and half cycle symmetry, the RMS value of the supply current is RMS of the discontinuous current. So, deriving this typically from this relation, total RMS will be 24.47, and input power drawn from AC mains will be ISC square plus E0 I0, that is 13,541.5 watt. So, fundamental RMS current from AC mains will be P upon 3 Vs, so that is 18.839, and supply AC peak current will be your Vsm minus E, so that is a 1 and it will be 46.89. The average DC current from this relation you can calculate keeping the value 23.9682 where R1 and VSM, and the RMS AC supply current which already calculated comes 24.47, and RMS fundamental current from power divided by this which we calculated earlier 18.39, and input power down from AC mains I square, that is also we calculated previously, and the total harmonic distortion putting the value it comes 82.894% like, and displacement factor because cos phi 1 is 1, also here case because there is a in case of phase with that, and the total distortion factor here from this IS1 upon this 0.76988, and power factor because your displacement factor is unity. So, it is same as 0.76988. So, you can call it this power factor reduction is because of harmonics, because there is no reactive power drawn from this, and crest factor will be supply peak current by RMS current. So, putting the value of this it will be 1.9166. So, in place of root 2 of 1.41 this crest factor increases to 1.9166 like in this case. Coming to example number 12, consider the 3-phase semi-control bridge converter shown in this with sinusoidal input supply line voltage of 415 volt 50 hertz and constant DC current of 50 ampere here. Calculate the distortion factor, displacement factor, power factor, total harmonic distortion for V output equal to 0.75 VD0, where VD0 is the output voltage at alpha equal to 0. Repeat part for part A for fully controlled converter. So, in this case you can see the current here, typically the kind of current, because of you can call it semi converter. These are 3 supply current and these output voltage, and these are typically you can call it the output constant current. So, given that the supply voltage is 415 by root 3, 239.6 volt, supply frequency 50 hertz and output current of 50 ampere. In this way, semi control converter, the waveform of supply current is from firing angle alpha to 180 degree with the amplitude of DC current VO equal to 0.75 VDC0. VDC0 is the DC current alpha equal to 0, then the firing angle of alpha equal to 60 degree. And putting the value of this semi converter, so you will get a RMS current corresponding to this 40.825 ampere and IS1 equal to this 33. For putting the formula value, it comes 30.73 and displacement factor comes cos theta 1, that is cos alpha 2 by 0.866, and distortion factor IS1 upon IS, that comes putting the value 826968, and power factor is corresponding to putting the both value of distortion factor, displacement factor and distortion factor 71615, and total harmonic distortion putting the value here, it comes 68.006%. So, this is also much higher, like 31% normally there in case of your 3-phase fully controlled converter. So, coming to the second part of it, I mean we have a thyristor converter with the highly inductive load, and this is the current quasi square wave with the supply voltage, this is the output voltage and this is the current. So, in 3-phase fully controlled bridge converter shown in figure, the waveform of the current is from firing angle alpha to 2 pi by alpha, that is 120 degree conduction with the amplitude of DC current, and if VO equal to 0.75 where VDC 0 at alpha equal to, then firing angle comes from this relation 41.41. I mean calculating from this for 3-phase fully controlled converter, and supply RMS current will be I or DC current into root 2 by 3 because it is a 120 degree duration out of 180, it comes 40.825 ampere, and fundamental RMS here will be your root 6 pi into I0, so it is a 38.8985 ampere, and displacement factor will be cos theta 1, alpha is calculated here, so it comes 0.75, and distortion factor is IS1 upon IS 3 upon pi 0.9549, and power factor will be displacement factor into distortion factor, so it comes 0.716, and total harmonic distortion of AC mains current will be your IS square minus IS 1 square under root of that divided by IS1, so that is 30.3108, so it comes 31.08% like. So, coming to another numerical example number 13, a 3-phase fully controlled bridge converter shown here used as a line commutator inverter to feed the power from battery with 360 volt and a internal resistance of 0.2 ohm. The supply RMS line voltage is 415/50 hertz and sufficient inductance is included in the output circuit to maintain the current virtually constant at 30 ampere. Determine the required delay angle alpha, distortion factor, displacement factor, harmonic distortion of AC mains current, curve factor and power factor, and AC RMS current. The typical here will fully control converter with a highly inductor and the battery connected here. So, you can call it here it is a working line commutator inverter feeding power from this side to this side, and these are typical waveform here. So, coming to the solution part of it, given that supply RMS voltage 415 by root 3, that 239.6 volt and supply frequency 50 hertz and I0 30 ampere equal to 360 volt and RDC 0.2 ohm. So, in 3-phase thyristor bridge converter, the waveform of the supply current is a quasi square wave with the amplitude of your DC current I0, and therefore, IS equal to root 2 by 3 into I0, 0.81649 I0, that is 24.49 ampere. Moreover, the RMS of fundamental quasi square is root 6 pi into I0, that is 23.39 ampere. And average output voltage from calculating this value, it comes minus 354 and alpha is corresponding to 129.17, which is more than 90 degree. It means it is working as a line commutated inverter, and distortion factor is IS1 upon IS, so it is a 3 upon pi, that is 0.9549, and displacement factor is your cos theta 1. Putting the value of alpha here, it comes like 0.6311837, and total harmonic distortion here from IS square minus IS1 square under root of that by IS1, it comes 0.3108, that is 31.08%, and crest factor is your peak upon RMS. Putting the value here, it comes like your root 3 by 2, 1.2247. It is still less than a sine wave, that is root 2, 1.4, and power factor is dPF into dF. Putting the value, it comes 0.60315, and AC mains RMS current, that is root 2 by 3, so it is your 19.8147. Now, coming an example of 14, number 14, a 3-phase a non-linear load is supplied from a 3-phase 415 volt and it consists of thyristor bridge converter feeding a resistive load of 15 ohm at a 45 degree of fire angle. Calculate the fundamental reactive power drawn by load, fundamental reactive power drawn by load, power factor, RMS current, supply current, distortion factor, fundamental RMS current, peak current of mains and total harmonic distortion of the AC mains current. So, after keeping the value of all and simulating, you have a supply current of this nature, output voltage and output current also of this nature. So, coming to given that the supply voltage of phase voltage will be your 415 by root 3, that is 239.6 volt and frequency 50 hertz with the load resistance 15 ohm and fire angle 45 degree. So, in 3-phase control bridge converter, the waveform of supply current is decided by the load resistance and fire angle. So, you can calculate from this relation, so it comes 22.589 ampere and RMS current of this load current from this relation will be your 20.725 and active power component of this will be P upon 3 Vs, that is 15.97 ampere and displacement factor will be cos theta 1. So, that will be your IS 1 A upon IS is 0.77073 and sin theta will be under root 1 dPf square. So, that is 0.63716 and fundamental active power drawn by load will be P. Calculating from this, so it will be your 11,481.667 kilowatt and fundamental reactive power drawn by the load will be 3 Vs IS and sin theta 1, it comes 9.491885 kVr and power factor will be your displacement factor, distortion factor displacement, so it comes 0.70711 and the distortion factor will be IS1 upon IS will be 0.9175 and the fundamental RMS current from this relation you calculate 20.725 and peak current from this relation will be your 37.793 and total harmonic distortion in this case comes like a 43.36, which is less than 48% in typically. So, it is in between like it, you can call it. So, coming to your numerical example 15, a 3-phase non-linear load is supplied from 3-phase 415 volt having a 12 pulse diode bridge converter with 200 ampere DC current. It consists of ideal transformer with a single phase primary star connected winding and 2 secondary winding connected in star delta with the same voltage and unity turns ratio to provide 30 degree phase shift between 2 sets of 3-phase output voltage. 2 6 pulse thyristor bridge are connected in series to provide 12 pulse AC DC converter. Calculate the fundamental active power drawn, power factor, RMS supply current, distortion factor, fundamental RMS current, peak current of RMS and total harmonic distortion. So, you can see this is the circuit here, what it is explained there. And now, coming to the solution part of it, after putting the all this and making a model, this is the virtually the waveform of 3-phase supply current with 3-phase supply voltage and the DC output voltage and DC current. Given that the supply voltage 415 volt line and now phase will be 415 by root 3 to 39.6, frequency 50 hertz and output current of 200 ampere in 3-phase 12 pulse diode bridge. The waveform of AC mains current is a stepped waveform as a first step of pi by 6 60 degree angle from 0 to pi by 6 and input current magnitude will be I 0 by root 3. Second segment will be step will be pi by 6 angle from pi by 6 to pi by 3 and input current magnitude will be I 0 1 plus 1 by root 3 and third step of pi by 6 angle from pi by 3 to pi by 2 and the input current magnitude will be I 0 in bracket 1 plus 2 by root 3 and it has a 4 symmetric segment of such a step of this current waveform. So, coming to the calculation of this, therefore, RMS value of 12 pulse converter input current is your IS equal to keeping the all value, it comes 1.577, so it comes 315.47 ampere. RMS fundamental current of 12 pulse converter again calculating will be double of that, it 311.87 and active power drawn from this will be P 3 Vs IS 1 cos theta 1, so it comes to 24.17 kilowatt and power factor is P upon 3 Vs IS, so it comes 0.9886 and RMS value of the current of input will be from this calculation. So, it comes again the calculator already earlier 315.47 and distortion factor will be IS 1 upon IS to 0.9886. Our RMS value of fundamental current of AC mains current will be your 2 root 6, so that be 311 and peak current will be of course I 0 1 plus 2 by 3, so that is 2, it is a 430 point this total harmonic distortion keeping the value here it comes 15.22, that is certainly half the or 31%. So, for 12 pulse converter you will not have a harmonics less than 11, you will be 11, 13 and 23, 25 that kind, that is the reason TID is reduced like. Coming to another example of 3-phase non-linear load is supply from 3-phase 10 volt having a 12 pulse thyristor converter with the 200 ampere constant current at 60 degree fire angle of thyristor. It consists of ideal transformer with single primary star connected and winding the two secondary connected in star delta with the same line voltage of 30 degree. Phase shift between two sets of 3-phase output. Two 6-pulse thyristor bridges are connected in series to 12 pulse AC DC converter. Calculate the fundamental active power down, fundamental reactive power down, power factor, RMS supply current, distortion factor, fundamental RMS current, peak supply current and total harmonic distortion of supply current. So, this is the typical circuit of that. You have a star connection, a star delta connection with two thyristor converter connected in series, and these are 3-phase voltage and supply current of 3-phase. The output voltage corresponds to that fire angle and the output current. So, coming to the solution part, supply RMS voltage is 415 by root 3, 239.6, and the supply frequency 50 Hz, and output current is your 200 ampere, alpha equal to 60 degree. In 3-phase 12 pulse thyristor converter, the waveform of current will be step waveform. First step pi by 6, that is alpha to pi by 6 plus alpha, and input current magnitude I 0 by root 3. Second step will be pi by 6 angle of pi by 6, and from pi alpha plus pi by x to alpha pi by 2, and input current magnitude will be I 0 1 plus 1 by root 3. Third step will be of again pi by 6 angle, that is from alpha pi by 3 to pi by pi plus alpha, and input current magnitude of I 0 1 plus 2 by root 3, and it has a 4 symmetrical segment of such a step. So, coming to calculation, the RMS voltage of from that waveform you can calculate the RMS. It comes like 1.5, so it comes 315.47, and RMS of 12 pulse converter fundamental IS1 from this relation you will get 311.87, and active power component will be IS1 cos theta 1, that giving a alpha value. So, you get a 155.93, and active power drawn will be 3 Vs IS1 cos theta 1, it comes 112.08895 kilowatt, and fundamental reactive power will be 3 Vs IS1 cos theta 1. So, it comes 3 Vs IS sin alpha. So, it comes 194.1437 kVAr, and power factor will be P upon 3 Vs IS. So, it comes 0.4943, and RMS of 12 pulse converter keeping the value which we calculated earlier, it comes 315.47, and distortion factor comes IS1 upon IS 98861, and RMS of fundamental gain from this will be 311.8786, and peak will be your I 0 1 plus 2 by 3, so it is 2.1547 into I 0 430.94, and total harmonic distortion will be 1 upon, so it comes 15.22%. So, 12 pulse is just half of that again less than 11th harmonics will not be there. The lowest harmonic will be 11, 13, then 23, 25th, that will the band plus 1 plus minus 1. So, coming to example 17, in a 3-phase line voltage of 415 volt 4 wire distribution system, 3 single phase load connected between line and neutral, having a single phase thyristor converter, drawing the 10 ampere here, constant current at 45 degree angle, calculate the active power consumed, reactive power consumed, displacement factor, distortion factor, total harmonic distortion, power factor, crest factor of AC mains and AC mains RMS current. So, after putting the value, 3-phase square wave current is here, and neutral current will be again a square wave, but 3 times the frequency of this of your this current, and this is the output voltage for each and the current like. So, coming to solution part, the supply voltage of 239.6 per phase 50 Hz, and out current 10 ampere and alpha equal to 45 degree, and the RMS current of this will be again 10 ampere because it is a square wave, fundamental will be 2 root 2 upon pi into I 0, that is 0.99 ampere, and the RMS active power component will be IS cos alpha, that is your 6.364, and that active power consumed will be 3 Vs IS 1. So, it comes 4574.422, and reactive power consumed will be 3 Vs 6 sin alpha, that is 4574.42, and displacement factor will be cos alpha 0.707, and distortion factor will be 2 root 2 upon pi, that is 0.9, and total harmonic distortion will be your like a square wave 48 points, and power factor will be this into cos alpha 0.676, and crest factor will be your peak upon RMS 1, and the AC source current will be 10 ampere, and neutral current is also that is square wave, but 3 times the frequency again 10 ampere. So, well, we will like to summarize now this what we did in case of this today chapter of nonlinear load. So, majority of the power quality problems are mainly created because of use of nonlinear load. These nonlinear loads draw no sinusoidal current from the AC mains, which consist of harmonics current, reactive power component of current, fluctuating current, and balance current, and these nonlinear loads are classified into different category considering the severity of created power quality problems, and number of practical examples of these nonlinear loads are given with a view of proper exposure of power quality problems like. And analytical study of various performance indices of these nonlinear loads is made in detail with several numerical examples to study the level of power quality they may cause in system. And since these nonlinear load cannot be dispensed due to many economic, energy conservation and increase in production kind of benefits, in such situation it is quite important to study the behavior of this nonlinear load to find out our proper mitigation technique for power quality improvement to reduce the pollution on the supply system. Thank you, and these are the some of the references with the thank you very much like on.